Okay, welcome to this afternoon's presentation, or at least in the UK time frame. If you haven't met me before, I'm James Pell. I lead turbine development here at OrcaFlex. I'm following on from David's presentation yesterday concerning what's new in version 11.3 for OrcaFlex. If you missed that, that will be made available through the website and the YouTube channel in due course, and I'd encourage you to check that out. There's lots of interesting stuff in there. I'm going to be briefly talking about what's new in the OrcaFlex turbine object, and just for the sake of clarity, that is still essentially what's new in OrcaFlex. We've just spread it across the two presentations, and then Chris is going to take over and tell us about what's new in OrcaWave for the remainder of the presentation, joined by our colleagues David and Colin, who will answer your questions as we go along, and then Chris and I will address any remaining questions at the very end of the presentation. So for the turbine, the big feature added this year is unsteady aerodynamics, aka UA for short. So when you specify wing type load coefficients in an OrcaFlex wind type, what you're giving there are the static or steady values. So this is the lift, drag, pitching moment coefficients that you might measure if you were to put the wing or airfoil in a wind tunnel or a CFD code, etc., at a fixed angle of attack. However, it turns out that if you are varying the angle of attack, if you're pitching the wing with a sufficient rate, then unsteady flow phenomena can mean that you can actually measure quite different values for the drag and lift and pitching moment for the same given angle of attack, so relative to the steady or static case. And this can become important for a turbine if it's operating in skew, sheared turbulent flow, or actually, for a floating wind turbine, if the floater itself is pitching or surging into the wind, for example. So to address this, we've added two models, Gonzalez and Minima-Pearce, and they're both based on commonly used BL models. And the implementation in OrcaFlex has been adapted from the work done by OpenFast, work done by NREL rather, for the OpenFast Aerodyne module. So the credit for the models goes to the guys at NREL, and of course also the original authors for which these models have been named. So let's just look at how you would enable one of these models. So I'll just add a turbine object here and open up the data form. See the turbine data form, and there's the now renamed page BEM and EUA. Previously it was just called BEM, and the new data lives here. And to enable one of these models, you simply select it. Obviously, if you select none, then no UA model will be enabled. When you enable it, that enables it turbine wide, but it won't apply immediately. You still have to come along to any wing types that the turbine uses, and in this case, because I've just added it, there's only one blank wing type, and enable it there. So when you enable it for the wing type, all parts of the blade using that wing type will use the UA, the unsteady aerodynamics calculation that you've chosen, the Gonzalez or the Minima-Pearce. Now, not only do you have to enable it, but you obviously have to also specify the associated data. As you can see, a lot of that comes with default values, which I suspect won't be edited a lot, at least whilst people are starting up with this. But there are data that is specific to the wing type or airfoil, and that will have to be specified before you continue with an analysis using unsteady aerodynamics. Now in the help, we describe what this data means, but we also give a reference for an NREL paper which discusses it in far more detail. But before we continue to look at any more OrcaFlex models, let's just go back to these slides, and I'm just going to try and describe what these models are trying to capture in a bit of detail first. So I'm sure you're aware that the aerofoil has a stall angle. So if you can see that plot there, that's a plot of lift coefficient versus angle of attack. And at some point, if you keep increasing the angle of attack, you get to a point where that doesn't produce any further lift. That's the static stall angle. And you can see that there. That's the static coefficients lift coefficients plotted in the black dashed line. It's quite faint, but you should hopefully be able to see around 13 degrees as a drop off in lift. And physically what's happening in a static stall is you're increasing the angle of attack. And as you do, the pressure on the suction side of the wing is reducing, which is desirable because it creates lift. But at some point, the pressure gradients become such that you start to get flow reversal from the trailing edge in the boundary layer. And as you keep increasing it, that reversal will lead finally to a full separation of the flow. And that's the point at which you're getting static stall. And conversely, in a dynamic stall, what happens is if you pitch the wing quick enough, then the separation occurs at the leading edge, and you can see the formation of a tip vortex, or a dynamic stall vortex, as it's called in that little diagram. And this tip vortex, so formation of tip vortex, and as you pitch it quickly, what you see is that you can actually exceed the static stall angle and still see an increase in lift. So that's shown on the blue curve there. So between points 1 and 2 drawn on there, you've pitched quickly, you've exceeded the static stall angle, but you're still seeing the lift increase. Now, at some point, that tip vortex actually leaves the tip and it's convected along the suction side of the wing, and it actually produces an increase in lift as it traverses the wing. And that's shown at 3 there. That's the peak lift. Now, once it leaves the wings, it shed off into the wake, and then you'll see full separation again. And that's dynamic stall. So that's 3 to 4, and it's characterized by this catastrophic drop in lift. Tends to be more severe than the static stall. And then also you'll see if you pitch the blade back to reduce the angle of attack quickly, that you'll see a delay in the recovery of lift. So that's 4 to 5 on that blue curve there. As you oscillate the blade, you'll travel around that blue loop there. So I've just got a little OrcaFlex model that tries to demonstrate that in OrcaFlex. I've got 2 turbine objects here. They don't look an awful lot like turbines because they're just, as we'll see, single segment blades. So it's really just a single segment of a blade. And I've given them a little pitch controller which just imposes some harmonic pitching motion. And there's a constant 10 meters per second wind moving from the right to the left here. So I just run the simulation. Should hopefully run quite quickly. And open up the workspace. Make sure I get the right one. Then I've plotted the same plot we had on the slide actually for the two turbines. I should probably just say actually the difference between the two is the so-called, the one I've named static has no UA model enabled, and the one named unsteady has the Gonzalez model enabled. The top one here is the static one, the bottom is the unsteady. Correspondingly, the top plot here is the lift coefficient against angle of attack for the so-called static one. I'll just play the simulation as well so you can see it going. See the blades pitching, increasing in pitch and then reducing pitch. And the bottom one here is the same plot, so lift coefficient against angle of attack for the unsteady case, so when we've got the unsteady calculation on. So for the top case, this is actually just tracking backwards and forwards along the lift coefficient data, essentially, that's been specified in this wing type. Now, for the unsteady case, the UA calculation is modifying that lift coefficient to account for these unsteady phenomena. So you can see that the static stall angle's just around 15 degrees-ish, but for the unsteady case, we actually go quite far past it, right up into the 20s, before you see this catastrophic drop in lift that we discussed before. And when the blade pitches back down, you can see that the lift doesn't recover to really quite small angles of attack. So that's what these models are trying to capture. And as the blade oscillates, it just loops around this hysteresis loop. Now, the exact path it takes around that hysteresis loop is strongly and non-linearly dependent on the amplitude of the pitching motion, and also the frequency of the motion. And I've tried to show that here. So this is a plot of that same study, if you like, that's that OrcaFlex model, where I've just changed the pitching frequency period. So the lines there, blue, red, green, purple, correspond to a period of oscillation for that pitching motion of 10, 15, 20, and 25 seconds, respectively. So that's the solid lines. The markers, so the crosses, circles, squares, and triangles, they're from a corresponding open-fast aerodyne model set up exactly the same. And as you can see, the results are, pretty much exactly equivalent. So hopefully you can see, the way it moves around the hysteresis loop is complex. It is dependent on these things, and hopefully you can also see that the implementation of OrcaFlex is consistent with OpenFast. But how does this affect a sort of less abstracted model, a sort of real world, perhaps you might term it, turbine? Well, here I've got a model of the IEA 50 megawatt reference wind turbine took from our examples. I've actually got two instances of the rotor here, unsteady and static. You won't be surprised to learn that the unsteady version once again has a UA model enabled. Again, I've gone for the Gonzalez model, and the static turbine, named static here, has no UA model enabled. Just for simplicity, I've disabled the blade degrees of freedom, so it's just a fixed, they're just rigid blades. I've disabled the pitch controller, not just for simplicity. I will come back and actually talk about why I did that later. And it's just got an imposed rotation for the rotor, so it just rotates at that reference wind turbine's maximum design speed. I subjected it to, I guess you might term it sort of stepped profile, but essentially it's got a 10 meter per second base wind speed, jumps up 2.5 meters per second after some time, then drops back down to 10. Then it jumps up to, 12.5, I should say, then up to 15, up to 17.5, and so forth and so forth. And on the left here, I've plotted the rotor aero LZ force for the two turbines, which is tantamount to the thrust force. And what you can see is that comparing the two, when the wind speed jumps, you see these peaks appear in the thrust for the unsteady turbines, the turbine that has the unsteady aerodynamic calculation running. Just to make the comparison easier, I've actually just plotted that on this slide. So shown here, the black line is just the wind time history plotted against the right axis there. But the curves we're probably more interested in are the thrust for the unsteady and the static turbines. They're shown in red and blue respectively. And so you can see quite clearly that when the wind speed jumps, obviously the thrust jumps, but you get these sort of pronounced little spikes initially for the unsteady case. Now, what's happening there is that because the pitch controller is off, as soon as you increase the wind speed, you increase the angle of attack. So it sort of swings the angle of attack out, if you like. And as it does that, it's going to put some of the blade past the stall angle, static stall angle. And bigger the jump, bigger the angle of attack change, more of the blade goes into static stall. And through the mechanisms we've been discussing earlier, that means when you have the unsteady aerodynamic calculation running, as you exceed the static stall angle, you actually still see an increase in lift. And that manifests itself in this model as these peaks in thrust. After some time, the way those models are set up, it decays back down to the steady, the static behavior, and that's why it tends back to the blue line after a few seconds. And as you can see, for the largest changes in wind speed, there's a really, really pronounced difference in the thrust. However, I just want to clarify that you shouldn't go away expecting to see, like you do there in that final peak, the thrust doubling or whatever, because that's not going to happen. I've gone out of my way to exacerbate the differences here, primarily by disabling the pitch control. This is a pitch regulated turbine, as most of them are, as opposed to stall regulated. And the whole idea is that, if you were running the controller on this, if the wind speed increases, then what the turbine wants to do is actually pitch the blades out and reduce the angle of attack to keep it out of stall. And and if it doesn't go into stall, then these effects aren't so pronounced. So actually, yeah, if you run this model with the controller active, you see those peaks are substantially reduced, and it's also a much more murky, complex picture because the controller is desperately trying to keep up with these very large changes in wind speed. I mean, that's the other thing. I've given probably really unrealistic jumps in wind speed there by the end. But anyway, it can be important in some cases. So that's the big step change in functionality for version 11.3 for the turbine object. We've also been doing some other pieces of work that I'll show you briefly now. The most relevant of those is probably that we've actually updating the KO3 50 megawatt example. The reason I say, and that's to reflect the latest revision of that's publicly available through the GitHub repository, which is version 1.1.3. Now, yeah, the reason I say it's relevant here is because as part of updating the data, we've also incorporated all the unsteady aerodynamic data for those wing types. So there's 50 odd wing types, it's a hell of a lot of data. If you try to do that manually, it'd be pretty annoying. I've used a little script to do it. We're going to be putting that out soon. I'm not quite sure when. It's basically done. It's just going through final QA process, maybe before Christmas, maybe just after the new year. We'll see, but hopefully that's going to save you, a lot of time having to set that data. Other data is also set for what it's worth for features that came out after the first edition of that example. So the shear center in the blade profile data is fully populated now as well. Alongside that, we're issuing a little validation document of that rotor, comparing it against the OpenFast model from the GitHub repository. We're looking at the blade dynamics and aeroelastic response for steady, stepped, skewed, turbulent winds. The comparison is very good, I should say. And as sort of as an aside, one thing that we've learned looking at that model is that reference wind turbine, the 50 megawatt, actually has an aeroelastic instability when you include a torsional degree of freedom in the blade, which is naturally always included in an OrcaFlex model. So it always holds for the full 6 degrees of freedom. And including these unsteady aerodynamic models, which affect the blade's damping, essentially, aerodynamic damping, can act to significantly suppress that instability. And as a result, it makes the models actually far more robust, so far less likely to fail due to extreme blade flutter. So that seems to be a sort of nice byproduct, as it were, of including these models in that reference wind turbine. We've added some small features actually to the software itself as well. For example, if you come and have a look at the properties report now, properties report is not new, but we now report the segment properties. So these are the values that have been interpolated out of the blade profile data. It can be a nice way of just checking your data, or at least checking how the data is being used by the discretized model. We've also just slightly extended the summary results. This is a very small change, but if you come to the summary results for one of the blades, then if I just can get down to it, we've just extended the segment properties report, the position of the aerodynamic center relative in respect to global. That's quite useful in statics mode to fix the blade, run statics, and find out exactly where the aerodynamic center is falling. So I've used that actually when updating the reference wind turbines recently, just to make sure I've set the pre-bend curvature up correctly. I'm landing the aerodynamic centers exactly where I'm expecting them to be in space. So very small, but can be quite useful for setting up models. On the turbine itself, we now offer the facility to scale the induction from the blade element momentum method between a lower and upper bound tip speed ratio. That can be desirable because the blade element momentum theory is less appropriate for a slowly spinning rotor. It really pre-assumes that the rotor is spinning at a sufficient rate. So now at tip speeds below the lower bound, the induction will be completely suppressed, and then it'll be scaled up to its full value by the upper bound. If you don't want that scaling, then you can set those values to 0, and the full induction will always apply. if you load up old data files, so a turbine model that's been built pre-version 11.3, that data will be loaded up with 0, so you don't see a change in behavior. So if you do want the change in behavior, then you have to come in and set that data, but it does default to 1 and 2 for a new model. And we've also added the skewed weight factor here. So this is in the skewed weight calculation for skewed flows. It modifies the actual induction factor. If you hit F1, you see the equation, how this factor appears in it, and it just gives you a little bit more control over that correction if you want it. Now, perhaps more significantly than those sort of minor periphery developments, we've done some work to optimize the turbine's calculation code, specifically the code that works to map the displacements or the motions and the loads and the derivatives between the solver and the blade structural nodes. It's always really hard to say like how much a optimization like this will influence a sort of real world model, as it were, because your model could be filled with all sorts of other different objects with features enabled and data set in certain ways, etc. So the bottleneck could essentially be somewhere else. But just to give you some indicative ballpark figures, I ran the what you might term the sort of OrcaFlex turbine example suite. So there's 3 examples that I'm sure a lot of you have seen that we distribute. 2 floaters, there's a spar and a semi, 1 fixed bottom. I also ran the KO3 15 megawatt with just the rotor only. And running those examples in the old and the new version, I've seen broadly about a third come off the run times. A little bit more for the case with the rotor only, because obviously the turbine calculation code is going to dominate there. So pretty positive numbers. Hopefully you'll see something similar. Some of my colleagues have reported similar numbers, but obviously we can't guarantee anything because it depends what's in your model. And also, just sort of to be transparent, the unsteady aerodynamic model of course requires more calculation, so that has an associated increase in runtime with it, but net between the two, confident runtime should come down a bit. And also, when you are running with that model, like I say, from the early work that we've done, it does appear that it does make the models more robust. So all in all, hopefully it's going to be sort of net positive for running your simulations in version 11.3. As for version 11.4, where we'll be going next, well, that in a large part is determined by the feedback we receive after these meetings. But if any of this stuff is of interest, then please do let us know through the feedback forms you'll receive, or anything else for that matter. Some of the things we're thinking about looking at is improved modeling for anti-clockwise or downwind rotors. That's only relevant for a small subset of people, but it's quite painful for that small subset, so we're keen to do something about that. Further development of the structural model, well, the validation report that we're actually putting out and the work we've done towards that suggests that's not the highest priority, but it would be nice to admit 6x6 matrices, because it is annoying to have to back out. If you're working from a data set in that format, then to take it from that to the OrcaFlex required format is a bit annoying. That's what I've been having to do for this reference wind turbine. And the user interface is associated with that, like looking at streamlining the way you input blade data, specifically the pre-bend curvature. So if that's what you're suffering with, let us know, and maybe we could do something about it. Subsea turbines are self-explanatory. Internalizing spatial wind. So this is rather than relying on external code like NREL's TurbSim to generate your full field wind files, do you want to see something internal to OrcaFlex? Are there other models that you'd like to see supported, like the manned spatial wind model? Are there other file formats you'd like to see supported? If there are, then please let us know about that. There is going to apparently be another reference wind turbine released publicly. When that happens, a 20 megawatt, we will hopefully look to take that and build an example OrcaFlex model out of it. But obviously we can't do that until it comes. But when that does, I think we'll probably get that done. And look at some separating ready damping and also internal yaw control. But just FYI, like we are updating the controller example package that we distribute to keep try and keep closer in step with the Rosca developments. But also, like we've added recently this year, a little yaw control example, but using constraints. But I think it'd be much cleaner to do it within the OrcaFlex object. So if that's something that you're interested in as well, then please let us know. So that's where we might be going, but like I say, it's dependent on your feedback. So that's all from me until I might chime in with some questions at the end. But other than that, I'll hand over to Chris, who will talk about OrcaWave now.
Okay, thank you, James. Yep, I will take over and share my screen with you. There we go. Right, yeah, so I'll talk to you about the new features in OrcaWave in the 11.3 release. The same advice as we usually give applies, which is that you'll hear a little bit of information in the webinar today. If you want more, then the place to go is the What's New section of the help pages, which here we are, is in the introduction section of the help pages. So the same headings as you'll see on my content slider here, but there are links into the detailed documentation, so you can get all the gory details. Right, let me go back to my slide. Okay, so yeah, let me begin, and yeah, likewise with James, we'll pick up any questions at the end. If you have questions while I'm going along, then type them into the Zoom Q&A. Right, dipole panels, number one, and that's the the largest new feature in this release. So I'm actually going to spend most of my time talking about that. What are they? They're a new type of panel, a new object in OrcaWave, and they're used to model, excuse me, geometries like these. So any situation where you have a thin surface, a thin part of the structure, so heave plates here and strakes on these platforms and spars, and the reason for having a new feature here is that these thin structures are problematic in a conventional mesh that you would use in a diffraction calculation, and the generic behavior is that you get unreliable results if you try to model these structures. Now, as with any geometry that you could imagine, it's possible to get good results by using a fine enough mesh. That's always true, but the problem here is that you would need a really huge mesh with tiny panels, because the panel size would be dictated by the thickness of these thin parts of the structure. So it's not feasible in practice. So instead, dipole panels are an alternative approach. And in this approach, the thin parts of the structure are treated as having exact zero thickness. And doing that gives you robust set of equations and robust calculation results, and there's no requirement for a particularly fine mesh or large runtimes. So I'm going to show you an example which is based around this platform in the top left here, which is a floating wind platform, and it's the subject of a 2018 paper by CMOS and others. So let me switch to OrcaWave and show you this model. So if I go to the mesh view, that's the same geometry from the picture in the slide, and in this OrcaWave model, the heave plates, I'll zoom in and show you them at the base, and these sort of vertical skirts at the perimeter of the heave plates, they're modeled with dipole panels, which are drawn in green here in the mesh view. And if I run this OrcaWave model, then the radiation and the diffraction effects of those thin parts of the structure are fully captured in the diffraction calculation and their influence on the wave field. And physically, what we're modeling here is a pressure difference between the water on the two sides. So the water above and below the heave plate and the water inside and outside this vertical skirt. And that actually is, in a way, that's a handy definition of what a dipole panel is in a diffraction calculation. So it's a panel that has water on both sides. in contrast to the conventional body panels that are shown in red here, where obviously there's water on one side, but the other side there's no water. It's the interior of the leg here, or the hull of a ship, or something like that. So how have I built this model that I'm showing you? Zoom out again. Well, the data is on the bodies page in OrcaWave, the key data. I've provided a mesh file, as usual, that has all those panels in it. And the new data item, which is new in 11.3, is this box here. So you specify some text, and there's a pop-out editor to give you a bit more breathing room. And you tell OrcaWave here which panels of the panels that it's going to find in the mesh file, which of the panels in that file are to be interpreted as dipole panels. So you can give a list of indices here or ranges like I've done, and when you hit OK, that's job done. You've identified the dipole panels. Now there is a subtlety here which I'm going to have to talk about for a little digression, and the subtlety is, if I go back to the mesh view, the numbering system in the OrcaWave mesh for the panels is not in general the same as the numbering system for the panel data that's in your mesh file. So for instance, in this case, this is a common occurrence, there are panels in the mesh file which it turns out are above the water surface, and so they're dry, so they can't be part of OrcaWave's calculation mesh. OrcaWave has to discard those, and so that inevitably means the numbering systems start to differ. And there are other mechanisms as well by which OrcaWave might insert panels or chop panels in two. There are a couple of different mechanisms whereby that can happen. So we have this confusion potentially of having two different numbering systems, and the data we ask you to provide here, the sort of natural data, is the numbering system in the mesh file, to identify which of those panels in the mesh file are dipole panels. So to help you with this, we've added a new option in the view option here, whereby you can view this this information, and you can potentially identify the data to use to identify your dipole panels, or else you can be using it for debugging and checking. So if I zoom in here on a particular part of the mesh, you've always been able to click this option. This is not new, panel indices. That tells you the number of each panel in the OrcaWave mesh. And new in 11.3, it's really added to be a convenience for people who are building dipole models. There's an option to display the index that's used in that input I was talking about. So these are the indices that tell you where in the mesh file the source data for each panel occurs. Yeah, that's a sort of related addition here. We're also in a minor release that we haven't quite done it yet. We're going to add that information, these mesh file panel indices, to the mesh details spreadsheet report, so you can export that information and you'll be able to interrogate it or write scripts to do so if you need to. We did actually have, totally aside from dipole panels, we did have a couple of users ask for that information to be available for other sort of diagnosing tasks related to meshes, so that there might be other uses for it as well. Anyway, that ends my digression about the index data that you have to provide. I've got let me go back to the default view. I've got a model here with some dipole panels in, and what I want to do is use this platform as a little case study to show you the contrast between dipole panel model like this and a model that uses a conventional mesh. So I'll open one of those up. The real world, according to the paper, the real world thickness of the heave plates in this design is 10 millimeters. So here's what a mesh and an OrcaWave model for that real world thickness looks like. So I'll have to zoom in here to show you this. We keep zooming, zoom, zoom, zoom. Eventually can start to see that there is, in this mesh, as I've claimed, there is a thickness to these. This is the vertical skirt, and there's a corresponding thickness to the horizontal heave plate as well. But it's really very small. Unfortunately, this model is not going to give reliable results, as I indicated earlier. So what I want to do is show you that, and then talk about the different options that are open to you. So to justify these statements, let me go back to my slides and show you some results. So I've got two graphs here showing two different result quantities and how those results vary for different thicknesses in the modeling of this platform and its heave plates. So the first thing to say is that the model using dipole panels, which is the results with the green cross here, that correctly quite easily picks out the correct zero thickness limiting value of these two results. But the models using conventional meshes and conventional panels, which are the results shown with the blue lines here, it's a different story. So I think the results look perfectly good out on the right hand side of these charts, but for thickness that's less than 10 or maybe 15 centimeters, these results are becoming unreliable, and that's definitely true of the real world thickness, which is 0.01 meters. That's somewhere down here in the numerical noise. But really everything in this zone on the blue line I would classify as numerical garbage, unless there was really strong evidence to the contrary. So I think these results, these little snippets of the results for this model, give a good demonstration that the dipole panel model is the superior choice. It's certainly a lot better than attempting to mesh the real thickness geometry in a mesh file. Good. So I think that's one point I wanted to show you, but there's a bit more to say. Having said all that, you can still model this platform using conventional panels if you're prepared to make a different kind of approximation. So if you're prepared to choose an artificially large value of the plate thickness somewhere out here in this region. And the paper that I cited, the CMOS paper, does exactly that, and they choose a value of 0.4 meters. Now, obviously, making that sort of approximation, you would have to check all the result quantities that you were interested in, not just the two that I'm showing you here for the presentation. But I'll gloss over that detail for now, and I'll go back to OrcaWave and show you a model and a mesh using that 0.4 meters thickness. So I'll tilt it a little bit and then zoom in, and you can see now there is an appreciable thickness to the heave plate and to the skirt around the perimeter. So in this different approach, the shape of the platform base is obviously different. That might have an influence to some extent on the wave field. Also have changed the displaced volume and the hydrostatic stiffness and buoyancy properties as well. So there are there are various changes to think about, but nevertheless, it might be a valid approximation. I think the main drawback of this sort of approach is that it's quite a time-consuming and quite a delicate task to choose an artificial value for the thickness that you're going to use by a sensitivity analysis, and it's quite time-consuming because there are a lot of result quantities to check if you're verifying that it's a valid approximation, and you also, it's quite time consuming to produce a large family of mesh files with different thicknesses to test. But nevertheless, that is the alternative, if you like, to using dipole panels. Let me go back to the model with the dipole panels in. So one final thing to note about dipole panels is that there's an unfortunate restriction, which is that the solve type has to be the simplest potential formulation only solve. That's not quite as bad as it sounds at first, because we've extended the results that OrcaWave can give you from that solve type in 11.3, and I'll talk about that in just a moment. But the bottom line is full QTFs are the only thing that you can't, the only type of result that you can't get now if you're restricted to this solve type. So if you have a structure like this platform with heave plates and you really want full QTFs, then I'm afraid you're forced to go down the route of modeling it with a probably a larger than real life thickness, and the sort of approximation that I talked about and that's used in that 2018 paper. But if you're not after full QTFs, it's possible to use dipole panels and skip that approximation. Okay, so I will move on then and start talking about the next item on my agenda, which is the extended results that are available in the potential formulation. So the 3 bullet points here in the what's new, and these are all motivated primarily by making results available to people who are running models with dipole panels, but they apply to everything, models of all sorts. So I'll talk about the first one of the 3, which is C-state RAO results, and I'll show you a model here that I've already run. You can see I'm opening a results file, and it's been run in potential formulation solve type. And this model, I'll show you the mesh briefly, is a container ship, a Panamax large container ship. It's a very large mesh actually, but there are no dipole panels involved here. This is just a conventional model that's going to be benefiting from this extension. So I've got field points out on one side to generate C-state RAO results. And if we look at the results in the tables, these you'll be able to see that these C-state RAO results include the velocity results, which previously, to get those results, you had to be running the solve type that includes the source formulation, but you don't require that anymore. So in a model like this, where there are no dipole panels involved, what's the benefit? Well, it's a performance benefit. So if you can run with the simpler solve type, there's a runtime improvement, and there's also a memory improvement, a reduction in the memory you need. This is quite a big model. I showed you in the mesh view there are approximately 20,000 panels in this mesh, so the runtime savings are appreciable. Now, of the other 2 items, the other 2 bullet points in the what's new section here, they're both strongly related actually, because they're both about these kind of fluid velocity results, but being used in different ways. But of the 2, I think the one that is more worthy of a mention is the mean drift loads via the control surface method. So I mean, this means it's now possible if you use this method to get mean drift loads in a solve with the potential formulation only. And I think this is worth a brief digression just to showcase a model that's using this method. So again, this is a potential formulation solve for that same ship. And I've now got a quadratic load calculation method available to me. And I've provided a mesh file for my control surface, and you'll see the control surface in the mesh view. I check the box, and it's the yellow box here surrounding the vessel. So you can do this now in the potential formulation. I wanted to mention this just in case there are people watching the webinar who haven't yet dipped their toe in the water and experimented with this calculation method, because it comes recommended. I think our experience is that we're seeing time and again that it's better than the pressure integration method. It's usually better, it seems, and in some cases it's significantly better, and that means it gives more accurate mean drift load results. So at the moment, OrcaWave can't automatically produce a control surface for you. We're working on that for the next release in a year's time. But in the meantime, unfortunately, you have to produce a mesh file to use, which obviously is an extra task. But even so, it's usually worth the effort. That appears to be the trend in the models I see. So I mentioned that in passing, really. End of digression. Okay, so motivated by dipole panels, there were a couple of extensions there in what you can get from the simplest of the three solve types. Briefly mention calculation performance, as James did. There are 2 bullet points here. You should see an improvement in runtime if you're using finite water depth, which in practice most people do. Might be of the order of 20 to 30%. That's the sort of improvement I've seen in my testing. The second bullet point is a reduction in memory requirement. This only applies if you've got certain types of panels in your mesh, but the interior surface panels are very common. And if you do, you might see an improvement of 10 or 20, maybe a bit more percent on the peak memory required per thread. That's geometry dependent, though, mesh dependent. So two benefits there which are worth having. And I'll quickly move on to mean drift full QTFs here. I'll show you the OrcaWave side of this feature. So what's new here is that if you're doing a full QTF calculation, and I'm going to talk in frequencies because I find that's easier, there's an option for you to save calculation time by limiting your QTF calculation to a band of frequencies, and that for some people saves a lot of time. But in response to users, what we've added here is this checkbox at the bottom that says, okay, I only want a band of frequencies, but I also want the mean drift, the 0 frequency QTFs to be included in my results. And that's useful if you want to perform a static analysis that includes these loads in OrcaFlex before the dynamic analysis starts. So there's a new item here which is in response to user requests. Okay, and then I think the next thing I want to talk about is Morison elements, where if you saw the webinar yesterday, you'll know that we have extended the scope of these Morison element objects in OrcaFlex, and there's a parallel development to keep the same functionality between the programs in OrcaWave. So let me open a model that's got Morison elements and show you it. this is the OC4 floating wind platform, and it's the same model I showed last year. It's taken from the examples on our website. The Morison elements here are the green lines, which are the rigid cylinders, and in this model they're representing struts between the different parts of the platform. What's going on here? Well, the struts are small compared to the waves, so their effect on the wave field is negligible, and they don't need to be included in the panel mesh. But we do want to capture the loads on those struts and include that in the equation of motion for the overall platform. So that's the job that the Morison elements are doing here. And the development in 11.3 is that in addition to hydrodynamic drag loads and drag coefficients, these Morison element cylinders can also now feel loads due to added mass force and fluid inertia forces, and you can provide coefficients for those forces here. And if I press F1 here, I will jump into the help and get an explanation of what these coefficients are and how to provide them. Yeah, I don't think there's anything else to say about that really. Morison elements were new last year in 11.2 in OrcaWave, and it's a sort of incremental development of them here to provide these extra loads that they can feel in addition to the drag loads we had previously. Okay, so that leaves me with just one more thing to mention, which is in the in the file menu. There's now a compare data option in OrcaWave, which for OrcaFlex users will be very familiar. The same functionality as in OrcaFlex. So you can provide two data files, or you can compare the current model in the program with a data file on disk, and it will show you in text format where the differences are between the two. So that's obviously not a calculation feature, but it's a convenience feature for organizing your files and your workflow. And that is the last item on my agenda to talk to you about today. So what I'll do now is I'll start to wrap up, and then I'll pass back to James, and if there are any questions in the Q&A, we can pick those up. But before I do so, I'll just make a couple of points. Most important of which is that if you have any questions, obviously type them now. But after the webinar finishes, you'll get an email at some point asking for feedback. So please do reply and give us your feedback. It's important for improving these webinars in future, and it also obviously guides future developments. So please do that. As James said, the recordings will be published online on our YouTube channel in due course. Right, so I think I'll stop sharing my screen and pass back to James if there are any questions in the Q&A.
Yeah, thanks, Chris. There is a turbine question remaining there from Roger Cart. He asks, shouldn't the thrust be proportional to the velocity squared? The static thrusts seem to be leveling off as gusts got stronger. Well, actually, that was a bit of a funny case because I disabled the pitch controller. With the pitch control on, so for that reference turbine, actually you expect the thrust to drop at higher wind speeds because it starts to pitch the blade and feather the blade out, which reduces the thrust. I can actually if I just share my screen quickly, hopefully you can see that. Oh, not yet, wait there. Hopefully you can see that now. This is actually from that sort of validation study that I was discussing. And this is the comparison against OpenFast for the 15 megawatt reference wind turbine. and this is the CT, which is the thrust coefficient against the wind speed. So that's essentially the thrust ratio to the velocity squared. And you can see initially that is indeed roughly constant, like you say, but then it actually drops off quite dramatically. And that's because the thrust actually drops off a bit as it pitches, and obviously the velocity squared keeps going up. Now, in that particular case, though, I had a bit of a funny case because I disabled the pitch control. But the thing is, still the turbine, when the wind speed increases, it's still going to go into static stall, and that's going to cause a big drop off in the lift. And then, and as such, you'll see a smaller component of the lift in the thrust, in the turbine Z axial direction of rotation. So I think that's what you see this leveling off of pitch. And actually, I was just having a quick look then, and see if I can find it. I've got here a little plot from a paper of the rotor thrust against wind speed for a pitch regulated case. This is what I was just talking about, which is how that 50 megawatt would normally be. And you can see once the controller kicks in, you see the thrust dropping off. But for the stall regulated case, it's not such a pronounced drop off, but you do see the leveling off. And actually, the way I was running the 50 megawatt with the pitch controller disabled is sort of almost tantamount to a stall regulated turbine. So I think the behavior we were seeing is actually expected there. So hopefully that's a satisfactory answer. And I see there's a OrcaWave question up for Chris now, so I'll hand back over to Chris.
Thanks, James. Yeah, we've just got one question on OrcaWave. So the question is about Morison elements, and it says if we have them in OrcaWave, don't we need to add the Morison elements in OrcaFlex as well? So yes is the answer to that question. So in terms of the programs, as I said, we've kept them in step, and the Morison elements in the two programs have got identical functionality. And if you run a case in OrcaWave that has Morison elements like the one I showed you, and if you import that into OrcaFlex, well, I mean, there are two ways to import data, as you may know, from OrcaWave into OrcaFlex. If you use OrcaFlex to open the OrcaWave results file and use the automatic process for the import, then all those Morison elements will get imported as well, and your OrcaFlex model will be set up with the Morison elements in place and ready to go. But the short answer is yes. Obviously, you want your models in OrcaWave and OrcaFlex to be consistent. So you should have Morison elements in both of them. If they're in one, they should be in the other. Okay, so I think that's all the questions that we've got. And if nobody has any last minute typing to do, then it just remains to say thank you very much for attending and for participating, and goodbye.